Hi everyone, I hope you're all doing well and are staying healthy. Welcome to our next Mind 444 remote lab session, and this week we will be studying the fan test stand, which we will use to record data that will allow you to generate a fan curve. As you've learned during lecture, a fan curve represents critical information in ventilation engineering. It allows you to match the airway resistance and flow requirements of your project on the one hand with the pressure and flow characteristics of the fan on the other hand. And then, in this case, the word project could refer to a mine as a whole, matching a large fan to an underground mine, or your project could be a smaller auxiliary ventilation system, such as we studied a few weeks ago with the bag line network here in the lab. You remember that behind me there. As we've been studying in the labs, fans generate both flow and pressure. Typically, as the pressure generated by the fan increases, the flow decreases, as shown on this general plot of Q versus P, or P versus Q. Okay, so we have here, this is just something from the internet. So we have the flow rate Q across the horizontal axis. That would be considered our independent variable. And here's the static pressure developed by the fan. So at zero flow rate, we have the highest static pressure. And at the highest flow rate, we basically have zero pressure. Now conversely, for your airway, either the entire mine or a smaller ventilation system, as the flow increases, so too does the pressure drop throughout the system. So this is the inverse shape from a fan curve. So we'll look at a system resistance curve here. Okay, this is actually from an HVAC application, but a lot of parallels with mine ventilation. So this is just our equation, P equals RQ squared. Nice parabolic shape there. Again, flow rate on the horizontal axis, pressure on the vertical. And as the flow rate increases, so too does the pressure exponentially. So the operating point of a fan in an airway system occurs at the match where the pressure drop in the entire system matches the pressure generated by the fan, and that determines the unique flow rate Q at that pressure. And I've got a composite plot here. Okay, so here is our fan performance curve that we looked at first, and here is our airway resistance curve that we looked at. Just ignore this plot. And here is our operating point. So at this point, the pressure in the fan matches the resistance in the airway, and that determines our unique flow rate Q. All right, hopefully I'll review for you. This is important because you will want to size your fan very carefully in any substantial ventilation project. Large fans are engineered to operate very efficiently at specific values of P and Q, but as we diverge from the design parameters, the efficiency can drop off, sometimes dramatically. There might be a temptation to go with an oversized fan, but that will cost more initially, and if it's not running in an efficient region of its curve, you'll pay more or even much more for power. Usually fans run most efficiently close to their maximum performance characteristics, and less efficiently when they aren't working as hard, so to speak. In our lab session, we're going to use the fan test stand wind tunnel, which is behind me to the left. This is built according to a specification called British Standard 848, and it's a very economical way to test smaller fans, or at least smaller in the realm of mine ventilation. It's basically a duct with some added features. The fan test stand operates as a suction system with a fan at the far end pulling the air through, so it will be operating at a negative pressure relative to the ambient pressure. At the inlet, we see an inlet bell, which serves to reduce the shock loss for the flow entering the wind tunnel, as we studied in our last lab session on the airflow demonstration unit. You can't really see it that well in the video, but we'll go over in more detail shortly. There are 4 static pressure taps around the perimeter in the inlet section, and from the static pressure measurements that we record there, we will be able to calculate the flow rate Q based on equations that are in that British Standard 848. Okay, about a third of the way down, we have a box into which we can insert restrictions that will increase the static pressure that the fan generates. We have different types of resistances, and we can use different combinations of them depending on which fan is being tested. Again, we'll go over those in more detail shortly, but here's one example, a piece of wire mesh that is inserted into the box. Downstream from the restriction box, we have a second set of static pressure taps, and these are used to record the static pressure that's developed or generated by the fan in response to the flow restrictions in the box. So we're going to be recording two static pressures in this lab, but they'll be used for different purposes. Very important to keep that in mind. The pressure at the inlet to the test stand is going to be used to calculate Q from the equation in the British Standard, and the downstream pressure from the restriction box is simply the static pressure P developed by the fan. So it is the P in the P versus Q plot. The fan is powered by a variable frequency drive. See if we can see that here. Okay, right here, this is the same setup that you used in the very first lab session when you learned how to calibrate an anemometer, but we'll be using additional information from the drive unit for this lab session to record the electrical characteristics of the fan. Now at this point I'm going to take the camera off the tripod and show you the fans and discuss the testing we will do. All right. Right now the 10 horsepower fan is connected to the test stand. We're going to record data for 8 different flow restrictions, and we will do this at a relatively low speed and then at a higher speed. And we've got our light there. We'll use that shortly to show you how we're going to measure the speed of the fan with the laser tachometer. Around the corner here is the first of 2 5 horsepower fans that we have. And as you can see, it's got a larger rotor diameter than the 10 horsepower fan, so it's connected to the fan test stand with this conical adapter section here. So we'll do the same thing with this fan. We're going to use 8 different flow restrictions to record 8 data points, again at a low speed and a higher speed. Finally, around here is our second 5 horsepower fan, and you can see that this one has a long cylindrical duct attached to it, and the duct is actually attached to this fan's inlet. So we will connect this duct to the discharge from the first 5 horsepower fan, the one that we just saw, which will itself remain connected to the test stand, and we'll have the case of 2 fans running in series. Sorry, got to change my page here. And you guys can just read along with me. So we'll have the case of 2 fans running in series, one feeding into the other. And in this case, according to the fan laws, we should see that the pressure doubles compared to the case of the single fan, but the flow rate should remain the same. If we have them running side by side, that is a case of 2 fans running in parallel, and we would expect to see the same pressure developed, but with twice the flow rate of the single fan, again, according to the fan laws. So that is the introduction to the fan test stand, and in the next video we will go into more detail with the setup and the instruments that we will use. And guys, thanks again for bearing with me. I still haven't learned how to memorize dialogue, but we're doing the best we can.